Okay, so it probably doesn't seem like it, but we're getting really close to being able to write down a general formula that will tell us how any nonlinear, including linear, optical signal will be created and will emit a field that we can detect. All right, so let me just remind ourselves of what this new thing that we added last time, which is a Green's function. Okay, remember it's basically like the plain old time evolution operator, but we just include in there a Heaviside function to switch it on at a value tau, at time tau. So I'm just rewriting this. I think I might have written it with like t minus tau or t minus something. Anyway, whatever you put in here is going to go here, right? And this is e to the I L tau, right? So this is useful for the case where the Hamiltonian and Liouvillean are time independent. Okay, so that's good. And just remember what the theta function does is it goes to 1 at the value when t is equal to, in this argument here is equal to 0. Right, so if you put t minus 3, then when t is equal to 3, that'll be 0, and that will rise at 3. Okay, all right, so then the point of all of this was that we could replace those u's with g's. Okay, so we're going to do that. Now, here's the plan. All right, the plan is we're going to get precise about what the interaction Hamiltonian is, what the H primed is. All right, and we're going to call this interaction, well, I called it L primed in my notes. I think maybe Mukamal calls it L int or something like that. I'm just trying to keep the notation as similar as I can across the other things. So the time independent part of the Hamiltonian, okay, is going to be minus E of t times this V operator, right? Now this is nothing other than a classical field. And this is the dipole operator. All right, so we have talked quite a bit about the dipole operator, dipole moment operator in Liouville space. Now we just have in Hilbert space. Now we have the Liouville space version of this. So that would mean if you had mu, the thing that would be, you know, in Liouville space, this is going to be like mu operating on something like A, like V, operating on A, which A is usually going to be the density, but it could be some other stuff times the density, for example. So that means V is going to be something like mu A, if V is operating on something like A. Okay, the commutator of A and mu. I warned you that commutators were coming, and this is why. Okay, so what we're going to do now is imagine the basic idea, the basic recipe, okay, is that we're going to think about where we have the time evolution operator can be written as a series and that we sum, right? So we can imagine thinking of this as like u naught plus u like 1 plus u2 and so on. This is with no perturbation. This is like one power of the field, 2 powers of the field, and so on. And whereas these are just those different terms in that Dyson series that we then truncate eventually. So if I imagine, for example, that rho to the n, not to the n, but rho with an n superscript, corresponds to the nth term of the time evolution operator expansion, like this, of course operating on the initial state, then I can imagine that I know that the full density operator is just going to be the sum of all of these things. Right, of course. Okay, so what we're going to do, and so the way we can think about this then, ultimately, we're not going to do too much about electromagnetism, but the idea is that the polarization in the material will be given to us by the number of oscillators, or number of things that do this, have this transition, times the expectation value of the dipole moment. Right? To get this, we need to know the state of the system at time t. We're going to have the state of the system at time t to some order. That's going to give us an order here too. So if it's linear polarization, it'll be the first order term evolving the density forward to calculate mu to first order. That gives us the first order polarizability, which is going to give us the first order generated signal field. That's going to give us linear absorption, and so on. Okay. So the nice thing about this is if you keep all the terms and just do the full formula, you can generate any kind of optical spectroscopy you want. Linear absorption, some frequency spectroscopy, Raman spectroscopy, 2D IR, whatever. As long as you can think of it in a perturbation theory way, which is going to be the case for almost anything that you do. All right, so then what we get back here is rho n, right, is going to be minus I over h bar to the n. So we're thinking of the each and every term. T0 to t, tau n, down, tau 2, tau 1. And now we simply replace these u's with the 2 times in them, right? So we had u, t1, t2, or let's do it the other way around, t1, t2, t1. This is going to become the g function, whoops, g, t2 minus t1, because that's what happens up here. We can either shift the time evolution operator, or we can use this Heaviside function to do the shifting for us. All right, so when we do that, we get g t minus tau n, because remember that was the last step. So of course we were writing like u t comma tau n. Then we put that in there, and now we're just changing the function to this. This is really equivalent. There's no approximation or anything. This is equivalent to u t tau n. Right? Why am I doing this? You'll see in a minute, because we're going to change variables, and it's more convenient to do this if I write them in these differences here than if I write them as arguments like that. Okay. All right. So then we have that. Then we have the Hamiltonian, or the L primed, right? Because L primed is going to come here at the location and time of tau n. So we're just going to put in what is it at that point. So it's minus e of tau n times v. Now, the v is the dipole moment operator. The dipole moment operator is not itself time dependent. We're not presuming that there's some time dependence to the actual meaning of a dipole moment, right? So this thing here is a constant, and this a constant operator. And this is a scalar. It's not even an operator. It's just a number that depends on the time tau n. Of course, in real life, the field will have a vector, the dipole moment will have a vector, and we have to worry about the scalar product of them in physical space. But let's not worry about that for right now. For right now, if you want to think about it this way, the field is aligned along the dipole moment of the molecule. Yeah. Okay, the next term in this series is going to be, of course, g tau n. See, I can't do it. Tau n minus 1. Right? And then we'll have another one of these chunks. Minus e tau n minus 1 v. And so on. All the way down to the last term, which looks like g tau 2 minus tau 1 minus e tau 1 v rho of t naught. Somewhere we have to have the initial state of the system, and there it is. All right, so this is what you get for one of the terms of the u's. You get this. Okay. It's the nth one. All right, so let's do this. What we're going to do is we're going to realize that, as I said, the e's are not Hilbert, they're not quantum mechanical operators. These are all scalar functions. They don't have operator-like behavior. So we can shove them all to one side, right? Because they can move. They're like the Tetris blocks that can go wherever you want. So I'm going to move them over. And maybe just to make it even clearer, I will write them in a different color. I have all these colors. I should use them more. What I need is a stamp for this. You spend a lot of time writing these integrals. That's why I always call them the dot integrals. All right, the integrals are there. We'll do the e's in blue because blue is pretty. All right, and so then we have e, right, tau n. Now, one thing we need to keep track of here, how many e's are there? There's going to be 1, all the way up to this one here. So there's n of them. There's going to be n amounts of e's. And so because all of the n amounts of e's are going to give us a -1 to the nth power. Right? That means that we can bring that -1 in here. So I'm going to show you what I mean by that. So because we bring the -1 to the nth power, that means we can put a -1 in here. That -1 cancels out this -1, and this whole thing out in front becomes plus I over h bar to the n. Right? So that's the prefactor now, because we sucked the minus e out. The minus e is just coming from the basic physics of how you have an interaction Hamiltonian. You have E times the electric field times the dipole moment, and there's a minus sign. So we put the E in there. The first one is that one. The next one is going to be E of tau n minus 1, and then dot, 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 all the way down to E of tau 1. And those are all of the different fields. And what's interesting, of course, you see that they separate from the operator. Then we put the operator part in. So we'll have G tau, T minus tau n, G, oh, I need the V's, of course. Oh, yeah. All right, so we have V, then G tau n minus 1, right, and then V, all the way down to the last one, G tau 2 minus tau 1, V rho T naught. And again, this has a very intuitive meaning to it. We start out in whatever initial state we have, then we hit the system with the density operator, then we evolve with the propagator, the field-free propagator, from tau 1 to tau 2, at which point we're going to hit it again. Put another V here if you want. And then, and so on and so on and so on. So field, field-free, field, field-free. Right? That is one term. All of the like algebra stuff is in here. And then here is the scalar stuff, which is about the field. Okay, now, why did we go through and make this switch to the green function? One of the reasons we went to the switch to the Green's function is because we can put in these 2 times in a mathematically easy to see way. If I left it in u's, I'd have to put back what u means, and then I would see that this time difference was in there. So by putting it in the Green's function, we directly see that this is a time difference. Okay, so let's draw a little time ordering sequence here. All right, so we have T naught, T1, T2, well, these are taus, of course, tau, tau, and so on, all the way up to tau n, and then ultimately t. Those are all the little chunks of time that we broke the time into so that we could do this time evolution. All right. So we're simply going to now define some stuff. So we're going to define T1 with the regular Roman T, I guess. And that's going to be the time interval between tau 2 and tau 1. Then we're going to call T2 the time interval between tau 3 and tau 2, and so on, all the way up to T sub n, which is T, the interval between T and tau n. And by that, and the sign, of course, is these are all positive numbers, so that T1 is greater than tau n. We always know that T is greater than tau n because of the time ordering of the exponential operator. They can never switch orders. Okay, so we end up with these n chunks of time. We have one extra chunk left over, but we can worry about that later. All right. So when we do this, when we do this, there's going to be a key point that we can change the limits of the integral. And I want to walk through slowly how you do this, because I remember when I first figured this out, it was not obvious to me at all how you do it. Probably to the good math people who know lots more math than I do, this will be very obvious. But for me, it took a while to figure out. So what we're going to do, first I'm going to tell you what we end up doing to the integrals, to the intervals, and then I will show you how we can understand it in terms of maybe a specific example. So what we're going to end up doing, so it comes from the fact that the Green's functions are 0 before they turn on. So if they're 0 before they turn on, we can actually extend the lower limit more or less however we like because there's nothing happening before they turn on. That's convenient. Okay, so the question is, how can we use this change of variables to our advantage? Let's take a look at the first order term. All right, as an example, and then we should probably see what's going to happen. So rho of 1, or rho 1 of t, will be I over h bar from t0 to t, d tau. There's only one internal time. We have one field. Remember, this is going to basically correspond to our linear absorption. We have one Green's function, and it's just t minus tau. And we have one application of the dipole operator, and we have our initial density operator. Now think about what the Green function looks like. It looks like a function that gives you field-free evolution whenever this argument is positive. Right? When it's 0, so when t is equal to tau, it turns on. So what does that mean I can do with the lower limit of this integral? I can set the lower limit of this integral to be minus infinity without changing anything about what happens in this integral because nothing will be affected by that. I'm just integrating 0 for a long time. What about the actual value of t being negative infinity? So what we mean when we say set t not equal to negative infinity, I also need to change it in here. So what is rho of negative infinity? All that means is the density operator that we had infinitely long ago. So what we mean by that is the equilibrium density operator. Well, that's good. That's how I want to do my experiments anyway, right? I want to have my system at equilibrium, and then I want to start studying with all these wonderful laser pulses. So this is totally fine. Okay, so what we can do then is by changing the limits, what we realize is that the important thing is the interval in time here, right? Not that I know the specific times. It doesn't actually matter. I could take this whole system and study it on Tuesday, and I could have studied on Monday instead of Tuesday. I should get the same result because I'm at equilibrium. Okay, so because of that, we simply have a time interval. So this is a really common thing that people do. You see it in time-dependent statistical mechanics, is that we go from a sequence of time points to a smaller number of time intervals. So what we do is we define T1, which we haven't done yet. We'll do that now. T1 is equal to t minus tau. Okay. Why T1? Because t's already used for this. We don't want to use it twice. It doesn't make any sense. And if we rewrite tau, of course, we can solve this equation for tau. So tau is equal to t minus t1. Okay, so what we can do, for example, is we could, first of all, we need to figure out what's d tau. Right, well, d tau is simply the dt minus dt1. But dt is a number, right? So there's no variation of t. So what we find is d tau is equal to minus dt1. Sorry, dt1. All right. So what we can do now is when we change variables, we have to take care of the volume element and the in the limits, right? That's sort of the recipe for changing variables. So we set the lower limit t naught equals to minus infinity, right? And so when we do that, this whole integral thing is going to be, all right, so first of all, we have, by switching from d tau to minus, or to dt as our variable for integration, we have to have a minus sign in front. I should have planned this out a little bit. All right. We have a minus sign, I over h bar. And that minus sign comes from that switching of the volume element. Okay, and so what we said was that the minimum time is negative infinity, right? So the smallest value that tau will ever have is negative infinity. So t minus that is going to be infinity, right? So this is basically saying the minimum limit, the way we're defining things right now, is infinity, and the upper limit is 0. So we sort of swapped directions, right? So you can see where this is going. In a minute, when we switch the order, we're going to change the sign. So we get this, and we end up with e of t minus tau 1, or t1. Okay, because why? Because we have tau here, and tau is t minus t1. Then we have the Green's function, and the Green's function is now t minus tau, and t minus tau we define to be t1. Then we have the dipole operator, and then we have rho of equilibrium, at equilibrium, which is time independent. The equilibrium density cannot possibly depend on time. So when we switch the order of the integrals so that it goes in the normal way from the lower limit to the higher limit, then we simply swap them and then we multiply by minus 1. As we, a minus b is negative b minus a. So what you end up with up here, I'll write it up here, is we get back the minus sign. We're going from 0 to infinity, which is to say that the gap, that the time interval goes from no interval to infinity, right? dt1, e of t minus t1, g of t1, v rho equilibrium. So we get this down to a time interval and a single value. Okay, so that you can see what we've done is we've replaced the integral limit from t naught to t with 0 to infinity. And that's what we're going to do for all of these. And we're able to do that because the Green's function ensures that we can set the limit to negative infinity and then realize that we only have these time intervals, and it works for all of the terms in the rest of our sum. Okay, what do I want to say more about this? I want to say something real quick here. Something that's kind of come up, but I want you to see it now so you're ready for it. Notice that this field, there's an interesting pattern here, which is that we have E, T minus T1, and G, T1. Right? Remember, T1 is the interval, the time interval. We define it like this, that we had before. And then this is this field. So whenever you see a function of one time variable and another function of that time variable with an offset on it, in this case the offset is t minus t1, then, and you integrate that, that's a kind of convolution. It's a convolution integral. If the two functions were the same, it would be like an auto convolution. In this case, it's like a cross convolution. And the reason why that's important is because convolution integrals have useful properties when you think about their Fourier transforms. If you want to calculate the convolution of a function, you can calculate the Fourier transform of each function, multiply them together, and then calculate the inverse Fourier transform, and you will actually have this. All right, so that's an important thing. Another thing that's important is very commonly, especially in ultrafast spectroscopy, we pretend or we approximate our field as being a delta function. Why do we do that? Because we have worked very hard to make short pulses. Now, what's the shortest possible pulse? A delta function pulse. And you could say, well, there's no way to make that. You need an infinite bandwidth, and that's true. But a lot of times the spectroscopy that we care about is actually completely encompassed inside the spectral bandwidth of our pulses. And so the difference you would have in assuming that you had a delta function pulse compared to not is actually pretty small. Why is it useful to have a delta function inside of here? Remember what we talked about is when you integrate a delta function times another function, which in this case is this Green's function, times v times rho equilibrium, which was just some function of t1. As long as the delta function peaks somewhere inside this integral, then what you do is you replace the value of this function with the value at t, whatever the offset is. Right? That was that f of a thing that I did before in delta functions. All right, so what this tells us then is if this stuff is important, and it is, it's going to be called the optical response function, then in a sense, if we have delta function pulses, we're going to be able to read out the value of the optical response function if we assume that our fields are delta functions. Okay, so that's where this is going, and it's a very common approximation. Of course, there's all kinds of reasons why it doesn't really work in real life, but there are also ways of correcting for it if you can characterize just how not impulsive your pulses are. All right, so we're going to stop, take a break there, and then when we return, we will actually start to write out the optical response function by making the correspondence between Liouville and Hilbert space representations of the dipole moment operator, because we need to be able to deal with that.